Okay, welcome to CUAHSI series on machine learning and hydrology. Today's presenter is Chaopeng Shen. Chaopeng is an assistant, hopefully soon to be associate professor at Penn State University. He runs the multi-scale hydrology process and intelligence group in the Department of Civil and Environmental Engineering. He has been working on hydraulic deep learning since 2015. His paper Feng et al. 2017 was the earliest known application of LSTM in hydrology for a big data setting. He has published multiple review and opinion papers on hydrologic deep learning. He is associate editor of Water Resources Research and Frontiers in AI in Food, Agriculture, and Water. Today, he'll be presenting long-term projections of soil moisture using deep learning and SMAP data. Take it away, Chaopeng.
Thanks, John. I changed my title a little bit. I included both this uncertainty estimation aspect, and also I would like to provide some perspectives of hydrologic deep learning. So sorry for the last-minute change. I'd like to first say thanks for my team members, including postdoc Dr. Kwai Fang here, who got his PhD from our group, and then we have Dr. Wenping Tsai on the lower right corner. He's a postdoc here. And we also have our collaborator, Dr. Dan Kiefer. And you guys can see on this Twitter handle, you can follow me. And I often tweet about deep learning stuff and hydrology stuff. And we also open sourced our code. All the code that you see here in this talk, you can find them on GitHub. All right, let's get into it. So the content of today, I want to talk about the uncertainty estimates for deep learning models for soil moisture projections, and integrating process-based models and machine learning models. So there are a couple of different frameworks, and I'm going to introduce one novel framework. I'm going to provide some of my perspectives on deep learning because I've done some review papers and opinion papers. I hope to share my opinions with the community. Okay. So some background about the application. We have the Soil Moisture Active Satellite Active Passive Mission, which was launched in 2015. It has a revisit time of 2 to 3 days. It senses the moisture-dependent topsurface soil moisture. There are many use cases for this data. You can use it to improve your weather forecasting and land feedbacks to the atmosphere. You can use it to improve runoff predictions. Normally, this is done via data simulation. You can estimate vegetation water stress and agriculture applications. And more importantly, we can use it to understand on the world scale, how does soil moisture really work? And actually, there's some recent novel, not recent, but interesting uses of this data. That is, you can use soil moisture data to infer precipitation. All right. What we want to do is to use deep learning models to mimic or learn the dynamics that is recorded in SMAP data. And the particular deep learning structure that architects were using is non-short-term memory. I think a lot of you might be already familiar with this because there has been a talk by Freddie 2 weeks ago, I believe. But maybe some of you are still not familiar, but this architecture is underneath the Google Voice, Google Translate, Siri, and Amazon, all this AI stuff. So what is novel about this, if you see on the right-hand side, normally the recurrent neural networks has only one state, whereas LSTM has a cell state and a hidden state. On the other hand, it has various gates. Input gate, output gate, forget. It's to control what information this network wants to remember, what information it wants to forget. So it's essentially a self-trained memory system. And we use it as a dynamic model, which is kind of not what it was originally intended for. But the benefits of this is that it's free from structural assumptions, and it can be used to correct feedbacks to the atmosphere. So before we dive into this particular application, I want to talk a little bit more about deep learning. Deep learning is a rebranding of neural networks featuring large capacity, hidden layers that automatically extract features, improved architecture and regularization techniques. and it is supposed to work directly with data. And there's sort of this couch with the AI community that don't want to do any processing with their data and just want to work with the raw data alone. What is a little different between deep learning and the original machine learning is that original machine learning, you have the humans and experts define these features for you, and they do a neural network on top of those features. Whereas for deep learning, because you start from raw data, you allow the network to extract those features by itself. Okay? So that avoided the necessity for expertise, and this is one of the major advances that allowed it to be so much easier to use. And you can see all these different architecture. It achieves this automatic extraction of features through this. If you focus on this B portion here, you will have this encoder and decoder. As you can see, it has to pass through that information bottleneck. And by passing through that information bottleneck and being trained to reproduce the input data, it's forced to extract that crucial information so that it kind of learns how to create a tool for itself. Okay? And then we have these different architectures, including stochastic decoder, autoencoder, decoder, and convolutional neural networks, and LSTM. And the LSTM is the one that we're going to use today. So this LSTM model, we feed it atmospheric forcings from NLS. Optionally, we can feed it land surface model out solutions. We feed it some static features like soil texture, slope, land cover, irrigation, depth of the water table, etc. We feed it through the LSTM, and we ask it to predict surface soil moisture. We do that by comparing and calculating the loss function against the SMAP level 3 passive data set. Okay, so this was already published in 2017. The results was phenomenal. We have a very high R squared comparing the LSTM solution to the SMAP solution. As you can see, the R, the correlation coefficient, for most of the continental United States is above 0.9. But it gets to be pretty bad here in the Northeast. But that is supposed to be the case because the SMAP is not supposed to work well really under dense vegetation. And you have a RMSC that is well below the current the design threshold, the design accuracy level of SMAP. And we examined how far can you, if you have limited data, is it able to reproduce a long-term trend for you? And the answer is yes. We trained the data for 3 years after SMAP becomes available, and we handcuffed it to three or more years in the past, and compare with the in situ data from the core sites, and it compares favorably. And in addition, also evaluate the long-term trend, because we think some of the in situ data is too small for comparing with SMAP, but the long-term trend should be comparable. So on the x-axis, you see it's on the slope measured by the in situ data, and on the y-axis is slope measured by LSTM, and they match pretty well. Yeah, it's within what we expect as an order of accuracy. So this is published in 2018, the 2 papers. So this deep learning is powerful. However, the question follows: can we estimate the uncertainty? Because a lot of people would say, okay, we do not understand deep learning. We don't know what's doing inside. So this thing we can do is to estimate how much uncertainty we're facing so that we don't trust this data blindly. And it's also uncertainty estimation is like the backbone of many applications, for including data assimilation and decision support. So we need, for various reasons, we need to know uncertainty. And the uncertainty estimation method for this deep network that we introduce here is derived from vision deep learning. It's called a Monte Carlo dropout plus an aleatoric term. Okay, so we short that as MCD plus A. Okay, so the fancy thing about this, normally in our loss function we have this sum of squared as our loss function. Now as an advance, we propose, again, this was proposed by Kendall and Gao in 2017, to have the model output or estimate a sigma squared to match with that pixel. So essentially, you try to have the network estimate what the error magnitude is for a particular site, and that's depending on that input x. Okay, so this is what is called the aleatoric term. because you cannot reduce this you cannot reduce this error. You can probably estimate its magnitude, but no matter how much data you have, you won't be able to reduce that error magnitude due to instrumental accuracy levels. The other type of uncertainty is the epistemic uncertainty. It comes from the uncertain model parameters, in this case, the network weights. It can be captured normally by like a Monte Carlo or ensemble type of approach. And here, this is called the Monte Carlo dropout. What Monte Carlo dropout does is that it obtains an ensemble and calculates the divergence of an ensemble. The dropout is a regularization technique that's commonly used with deep learning models. When you're doing dropout, you're randomly zeroing out some of these connections. You're disabling some of these connections. It has something to do with, in my opinion, this has some connections to biological systems, like our biological systems. Sometimes part of the system doesn't work, and overall the system needs to function properly. In case there's some damage, it should still work, right? So we kind of enforce that. We force that condition during training. So after that, you get a much more robust system. So for Monte Carlo dropout, during forward, we will still apply this random connection dropout, this random zeroing out of the connection. Okay. So as a result, you can get an ensemble that the divergence of which quantifies the uncertainty. Okay. Right. However, this seems very appealing. Now, there might be many issues with this too. In 2016, Gao argued that neural networks plus Monte Carlo dropout is equal to deep Gaussian processes. Essentially, instead of taking the weights as one value, you put a prior distribution on these weights, and you take a look at the posterior distribution. But there are many issues in that derivation. This is really a very approximated, crude derivation, because you have to use certain prior. It's actually a standard normal distribution. And you have to use certain variation of distribution, which is like a normal distribution with a very small variance. Okay, so I won't show you the derivation here because it's very long. I can assure you don't want to read that now. It requires a hyperparameter because if you worked on this, you'll find out that the uncertainty estimate is actually a function of this dropout rate. So it's conditioned by your training data. A big question is, does it really measure similarity? Because if you're talking about a deep Gaussian process, it must measure similarity like Gaussian processes do. And although this paper has been cited 800 times, apparently having a huge amount of impact everywhere, I rarely see any people, first of all, evaluating quality as well as figuring out whether it is a Gaussian process or not. So that's a big question. And does this method accurately reflect the uncertainty? So these are a bunch of questions that we want to answer. So the overall approach is to have the model output a aleatoric term, and then we take the model and run many forward instances of dropout. We get this ensemble of simulations of the standard deviation. We call it sigma MC, and we basically, for the combined uncertainty estimate, we take the square root of the sigma x squared, which is this aleatoric term, plus sigma MC squared, and we know that this is a function of the dropout rate. Because there's a hyperparameter to tune, what we do is we train it in 1 year. We use 1 year of data to tune that hyperparameter, beta, the dropout rate. In reality, we take a very lazy approach. We find out one hyperparameter that kind of works and then stick to it all throughout our exercise. And we report the metrics in the 3rd year. So this is a map that shows the distribution of sigma x in the continental United States, and the tests are unbiased RMSD and the combined errors. As we can see, it gets a bigger error in the east because the rainfall is bigger in the east, and much bigger in the northeast because it also has a large forest and the vegetation water content, and SMAP has a large errors there. So what is very striking to me is this model, although it's not supervised by the uncertainty, it completely has to figure out that uncertainty by itself. It correctly predicted a larger error in the northeast. So that's kind of amazing. And it correctly predicted this big gap here between the high plains and the central low plains. So this was without any advice, any supervision of the uncertainty. It has to implicitly infer it by itself. And then if we look at how the quality of this, the sigma com versus the unbiased RMSE, we see an R of 0.88 for uncertainty 0.84. Sorry, for uncertainty estimate, this is a pretty good result. However, sigma MC itself would actually very much underestimate the uncertainty. All right, so we answered some additional questions. Does the sigma X uncertainty really respond to aleatoric noise? And sigma MC should not respond to it. So to answer this question, we added white noises into our observations and see how this uncertainties respond to that. As expected, this blue box, which is the aleatoric term, it follows up with that added noise. What that means is that this noise, this sigma X term, is able to pick up that aleatoric noise. So far it looks very good. What is not so perfect is that your sigma MC also went up a little bit. So there's a little bit of correlation, which I hope not to see, but this is not too bad. I mean, it's a weak correlation. We think that when you add more noise to it, you simply have less accurate data for your supervision. That adds to the complexity of the training, so that increases your sigma MC error. So that's understandable. It's not perfect. The second question is, does the epistemic uncertainty behave like a Gaussian process? So when we trained the data in one of the HOCs, one of the HOC2s, one of the subbasins of the United States, we noticed this very clear trend, that the errors are much smaller near that training data and much bigger further away from it. It doesn't matter where that training HOC is, in the east or the central or the west or the southeast, southwest. This happens. This is always the pattern. And here we show a very solid proof that Monte Carlo dropout does respond to similarity. Previously, it was hard for the AI applications to show this because it's hard to measure similarity in the first place. But here, through this autocorrelation in our input space, we showed this geometric proximity, this similarity corresponding to geometric proximity. So that's very encouraging. At least those two uncertainty terms behave as they're intended to, sort of. So we wanted to see how a biased training data set would influence the uncertainty quality. Okay? So in training experiments, we have our training data scattered throughout the U.S., but for the first three experiments, we have the four HOC2 basins scattered around the U.S., so in an evenly distributed way. In the last three, we have the training basins to be scattered in one side of the basin. Okay, now things become interesting. We see in this blue box, this is sigma MC that was inferred when the training data is concentrated in the northwest. Because it has only seen that small data in the northwest, it has not seen the bigger data in the east with more precipitation. So it thinks that everyone should have a small error. Okay, this is the same case with the sigma X. Okay? That means that our error estimate of sigma X is influenced or conditioned by our training data. And that means if you have a very biased training set, you can mislead this sigma X predictor. Fortunately, you don't have to be too comprehensive, too representative. If you have a spread like this, although there's a gap in between, you can already see that this error is more agreement with the actual error. Okay, so in more agreement with actual error, and we can quantify that uncertainty by looking at the error estimate as a probability density, as a cumulative density distribution. The ideal case is that it scatter around this one-to-one plot. When we are somewhat scattered, we have these lines in the middle, which have higher quality. But if you're really biased, then you have this blue curve, which is far from this one-to-one line. So we also try to kind of scale this sigma MC, this Monte Carlo dropout error, by that sigma X, so that gives us an indicator of how big of a surprise the test set is with respect to the inherent estimated error. And we do see there's a clear trend. When this metric goes up, your uncertainty goes up, except for this one. It's a little flat. The others all behave like this. Unfortunately, this did not collapse onto the same curve. If they did, then we would have a good metric of estimating the uncertainty quality. Okay, sorry, the y-axis is the uncertainty quality, which is this distance between the two, the distribution and the one-to-one line. All right. So our conclusions were 20 minutes in. Oops. And we have an amazing setup where the neural network can automatically estimate the error model. I think this is a hugely disruptive thing for uncertainty quantification, because you have a very intelligent network trying to figure out that error for you. Instead of you making the assumption Gaussian error model or other type of error model, it figures it out for you. We showed that sigma x and sigma c mostly works as intended. It's kind of a new, I think it's kind of a new finding because it wasn't very much verified before. Through spatial correlation, we do see that sigma c does measure similarity. When training data is representative, the Monte Carlo dropout plus A is good at predicting the error. So that works. However, it requires a hyperparameter tuning. If the training data is biased, the sigma x squared could be misled. So often this evaluation was not thorough. So this means that the uncertainty estimate is not a replacement for data collection. You have to have the representative training data. And some of the results that I did not show here is that the better prior leads to better results, better error models. Just a heads up. So we have some relatively new work where we implemented a closed loop LSTM, and this one shows a much more improved result compared to the old one. So this one is really very new. So we got it very recently, but I think it's very encouraging. So there's still a lot of room for improvement as compared to the standard LSTM. All right. So now I'm going to talk about another topic. Is that how do you see the integration of process-based models and machine learning? This deep learning model, since it's so powerful, can we use it to replace and essentially, to such an extent, avoid process-based models? My answer is no. Here's a breakdown of the strengths and limitations of process-based models and big data machine learning. For process-based models, it's built from the bottom up to observe emergent patterns. Okay, so that's a strength. We know what we put in. That's another strength. We can do experiments and identify causal relationships. Okay. The limitations are we have huge human bias in terms of choosing which model we use. We all know that. There's a lot of effort you have to put in for parameter calibration, and there's a lot of parametric uncertainty that you cannot get rid of in the end. What if there's processes that we don't know? Then you're going to have structural errors, which leads to all kinds of compensation in your calibration and all kinds of distortion in the meta dynamics, and that we don't know those things, and we could be biased. And these errors compound, making it incredibly hard to diagnose what the problem is. For big data machine learning, it's built from the top-down approach. It's directly from observation. It's very accurate. It's oftentimes tend to be accurate. It's less biased. I'm not saying it's purely biased, but it has less human involvement in it. So it has the potential to identify things that we don't yet know, because you don't have to encode any prior knowledge into these networks. It's highly efficient in computation. A lot of the computation, even for a very large network on the GPU, is a fraction of the cost of the real process-based model CPUs. The limitations of this are also myriad. You have it's very difficult to interpret, and then you can't observe everything. You simply cannot build deep learning models for everything because you can't observe them. It may not fully respect physical laws. You have to implement a lot of things in order for that to happen. For physical laws to be respected, it does not understand causal relationships. And this is one of the major deficiencies. So one day, if we got ruled by our robot overlord, this is one thing we can take advantage of to break their rule. Just kidding. Okay, but I see there's a lot of synergy between these two folks. And there's been a line of work loosely gathered under physics-guided machine learning. And there's many avenues where that could happen, but one of such is that you can literally encode physical laws in your loss function, for example, energy conservation or mass conservation. And this is work published from Wisconsin, Virginia, Virginia Tech and Wisconsin, where they encoded the energy conservation into the network. And these kind of networks tend to generalize better. However, this approach only works for very simple cases. You have a simple rule that you can encode. What if your model is like this? The community land model, there's probably about 100 governing equations there. Combine it with the 3D subsurface reactive transport model with a network of river channels. This becomes really, really, really complex, and you cannot possibly code that into your loss function. So to show an example that motivates our work of this new avenue, of this new framework, we talk about this background application, which is called the storage spring flow correlation spectrum. Essentially, this is a hydrologic signature. What we did is this was published in 2017. We take the maximum and minimum of the Grace terrestrial water storage, and we correlate it with the different percentiles of flow in a year. Okay, so we calculate the correlation between TWSA and the QX for different x's. The x is the percentile of flow in a year, and that is a rich set of dynamics that we can study and inspire hypotheses. For example, we classified all these different responses into 6 classes over continental United States. We see a strong spatial gradients in these and a strong diversity. For example, these green basins in the Appalachian, which is where I am right now, has low correlation coefficient between the TWSA peak and the stream flow. Okay, but higher concentration, higher correlation between TWSA and stream flow for the trout and low flow. Okay, but peak flow is always very poor. These blue basins in the south, they have very high correlation throughout all bands. Okay, this x-axis is the band, is the different flow percentiles. So from high flow to low flow, they all have very high correlation. So the question is why? Why do we have such a distinction? What is the physical reason for that behavior? So in 2017, we ran an experiment that told us that the rock depth or soil thickness is the main difference between those two clusters of basins. And it's easy to interpret because you have more soil thickness. You could store more water, leading to more saturation excess, larger flows. However, when we redo this again with more details, and we look at some of the slightly weaker models, you have a silt model, a criterion based on silt, and a criterion based on slope. These models, they can also split the two clusters. They are a little bit weaker, but the difference from the top one is not statistically that significant. And I would say those two are also behavioral models. So here's the limit of machine learning. It cannot tell which is the causal factor, which are the coincidental factors, because these factors co-vary in space. And we're opportunistic in the sense that we work with the basins we have. We can't create new cases. Okay? So what do you do in this case? We propose this framework where we take the machine learning models, we take the big data, pass it to machine learning, which generates data-centric hypotheses, and then we pass through this hypotheses, run causal determination experiments with our process-based model to figure out what is the real cause and which are coincidental factors. So we set up our experiments in the Susquehanna River Basin, which are one of those green basins you see. And you can see here most of these subbasins are belonging in the green class. Okay, so this basin by default has a very thin soil. So what we do is we run perturbed experiments with the hydrologic model that we set up for this region. We can increase the soil thickness, and we can increase the slope, and we can change the soil texture. We can assess which one is actually the causal factor. So long story short. We implement this through a process, our model, which is called PAUSE-CLM, which solves the Richards equation. So it has a representation of that physics. All right. So long story short, for all of these simulations, when we increase the soil thickness, these green basins would turn to have much higher correlation, and then they would behave more or less like those blue basins in the south. However, when we change the slope or change in the soil texture, there's barely any response in this SSD signature. And this way, we can pretty much nail down that the soil thickness is the main causal factor, and the other two are essentially coincidental factors. Now, we can actually formalize this into a data-centric Bayes law. Okay, to quantitatively do this, we can write it in a Bayes law like this, where the F is a factor that we want, are the list of factors that we want to assess. Y is the observed pattern. So in this case, would be the SSCS correlation. So the P of F, okay, that's the prior. It's the prior probability of an explanatory factor being the causal factor for the observed differences. And that can come from the cart, just like what we did. We have multiple competing hypotheses. A lot of the factors would be getting 0, but these 3 factors, soil thickness, soil texture, and slope, they would get a relatively high prior. The Py over F, then, is likelihood function. Given the change in the factor F, given the experiment we run by changing that factor F, the process-based model will generate the likelihood that the process-based model generates the observed data, observed pattern. And this can be assessed using a Gaussian mixture model of the outcome of that process-based model. Py is to be marginalized out, and Pf over Y, this is what we are pursuing. This is given the model experiment's results, the probability that factor F is the causal factor leading to the observed class membership. Okay, so here, what is very efficient is that we do this through machine learning that gives us a list of data consistent hypotheses, so you don't have to examine all the various hypotheses. For a lot of the previous Bayesian effort, you start from a model and you perturb the parameters of that model. You examine the posterior likelihood function of those models. So you spend a lot of computation effort as well as you don't even know where to start. So you're just randomly throwing a dart. Here, it's much more targeted because the machine learning is going to give you a very small subset of factors for you to look at. So it's much more efficient and much more unbiased. So we call it data-centric Bayes law. And what happened is a lot of these basins are class number 2 or class number 4 and number 3. And as we change the thickness, soil thickness, they all become class number 1. Therefore, with this likelihood function, we have this factor is nearly 1 for soil thickness, and it's nearly 0 for soil texture and slope. So that can quantitatively determine the causal relationships. So the conclusions out of this exercise, I hope I didn't go too fast on them, is that the hypothesis that large soil thickness causes higher storage stream flow correlation is true, whereas the other factors are only coincidental factors. The data-centric framework is only one of the possible options to integrate data and complex process-based models, but it's a plausible one. I'm completely sure there are many other frameworks for us to explore. This framework is highly efficient and more objective. Okay, so let's now move to the third section of this talk, which is about some of the perspectives I've gathered in the past about machine learning and some of the more recent work that we're doing. So on a bigger scale, if we go up on 30,000 feet, where are we at in terms of hydrologic deep learning? So I did this little report out to the AGU last year during the AGU talk, during the AGU conference. I did a little statistics on the deep learning in non-computer science disciplines and the deep learning in computer science disciplines, and I look at the machine learning in non-CS, the machine learning in CS, and I look at the fraction of deep learning, the ratio of deep learning versus machine learning. As we can see, for deep learning, it grew almost triple year over year from 2012 to 2014. In 2011, there was 0. Oh, there was a few in computer science, okay? And then, starting 2012, it started to triple year over year. This is a very fast growth, very fast growth. And then in 2015, it started to double instead of triple, because you cannot do triple every year, right? It's just, it won't sustain forever. But if you look at the AGU, the number of abstracts submitted to AGU that has deep learning in them, it was 18 in 2016, 15.8 in 2017, and 167 this year. So you can see this is a triple year-over-year growth. I would say that the geoscientific community is just waking up from their slumber. We we are approximately here in this red rectangle where computer science are. So we are probably around 3 to 4 years behind. Plus, these are abstracts to a conference, so there's still some lead time there. So I'm thinking about we are probably 3 to 4 years behind the computer science. So we're comfortably looking at several more years of growth after this. Okay. So there are many things that we can use deep learning to do, and I summarized these in my review paper on water resources research. And I just give you a small list of this. The first thing is we can use deep learning to model challenging to model problems, which are like human dynamics, where there are not even a governing equations for you to solve. And human psychology, there's this discipline called social hydrology, the pendulum change in human sentiment. Those things, there's not even a reliable governing equation, and you can probably model that using deep learning, and you can also use it to model, ecology. Those things, some of them are hard to model things. Then we can use deep learning to prepare inputs. For example, this is a standard thing now. There's almost a mainstream technique now. The remote sensing community en masse are using deep learning to extract features, and we can use those features to constrain our model or provide inputs to our model. We can use that as a dynamic predictions, as we presented previously. And this is one figure that I take from Frederick Kranzer's seminar last week, I think 2 weeks ago, where he showed a significant advantage of LSTM over Sacramento SMA model. And then we can use deep learning to solve some of the nemesis challenges, those challenges that have never gone away from process-based modeling. For example, scaling is one. We've done scaling, soil moisture scaling previously using property orthogonal decomposition. Okay, so for that PLD reduced order model, what we do is we kind of memorize some rooms from this from some PLDs from the simulation, and really it's a memorization of eigenvalue decomposition of this thing, right? But it cannot be applied elsewhere. It cannot be applied elsewhere. So what we're doing right now in our lab is that we train a new deep learning-based model where we have a coarse model and we have a fine simulation, and we try to predict that fine simulation using the coarse model. And it turned out to give us some very promising results. Can essentially achieve this downscaling with a very small effort. So you don't have to run this very fine scale resolution models anymore. You can just run the coarse model and couple it with a deep learning model. Okay, so this work is ongoing. We can use deep learning for parameterization. We can use deep learning to measure information content of some of the predictors, and that relates to some of the work that Gray Nearing did, where he measured, we partitioned the different sources of uncertainty to these errors. To input uncertainties, parameter uncertainties, and model structure uncertainties. But deep learning is a great tool for that. However, what I'm most interested in is, can we use deep learning to extract knowledge? We've previously discussed that a major advantage of deep learning is that it's able to extract features by itself. So extending that concept to scientific discovery, can we use machine learning to extract features that we don't know yet? And if we have some suspicions about this capability, we need to look at this historical figure, which I believe in probably 100 years we're going to come back and look at this picture again and think this is one of the watershed events in human history. Probably exaggerating a little bit, but that's my take on this picture. So this is the AlphaGo match, the famous match between AlphaGo and Les Sedot. And that's practically the one match that wake up a lot of people. And this Go game that they're playing is extremely complex. We know it's very hard to fathom that complexity. You know, the number of atoms in the universe is you raise 10 to the 82th power. It's a very large number. We cannot possibly fathom. But the tree complexity of the Go game is 10 to the 360th power. Okay. that's beyond the wildest imagination of what that actual number actually means. It's a very complex game. However, the deep learning model that AlphaGo they trained for this purpose, where they have a policy network and a value network, okay, that's basically assessing how strong you are in your current position, and you have a policy network to help you make the next decision. So that value network can actually give you a very good insight across a game of this complexity. It's astonishing. What is very interesting to me is that some of the comments from one of the Go masters, he said, okay, this machine played some moves. If they were made by my students, I would have fired these students right away, because those moves are just so elementary, and no students with any education would do that. So humans think those are bad moves, but AlphaGo nonetheless made them. It doesn't have a bias. It doesn't have a face. Then some of those moves turn out to be really good. So it occurs to me that these networks, these deep networks, certainly have the capability to extract very deep concepts, very abstract thinking, and even style. Right? So based on that thinking, can we propose a different avenue where we have data, we pass it through deep learning models, okay? Then we have the deep learning models to generate this data consistent hypotheses for us, and then we sort of like what we did just now, but we pass these hypotheses to the scientists to further discuss, and then we iteratively refine this process. Okay, the thing what is missing here is this interpretive method. We need to be able to know what the machine learning models deep learning models are doing, and this is really hard to do. Like, it's really hard to figure out what it's thinking about. However, throughout these different scientific disciplines, I've found people have different ways of tackling this problem. And for example, this is a very high-profile research done in neuroscience. They trained these agents to navigate, and then they built this network architecture, okay, to learn from those navigation data. That they first take some mouse, and they learn from the behavior of the mouse, and then they do reinforcement learning. What they find out is that one of these intermediate layers provided these grid-like structure. Okay, this supports a Nobel Prize winning theory, which is that the grid-like structure in the mammalian brain is the navigation device for our brain. And this was previously a theory, but this study by DeepMind provides a very strong support for that. It seems to say that such structure would automatically emerge if you have a navigational task like that. Give you another example. This Shoot et al. 2017, they trained a purposely built deep network. Essentially, they are mimicking the molecular structure. And then they try to use these structures to predict the chemical molecular properties. They showed that the network, they grasped chemical concepts by itself, even though the only supervising data it had was to predict the total energy of the molecules. It still grasps the concepts like rain that you see here. So, all right. So it was able to provide a classification of the molecular carbon ring stability that was never in the supervising data set. Another example, and I believe these are the sections that people don't have bandwidth to go into, but it's really like an underappreciated part in the review paper, in my review paper. In high energy physics, the Oliveira, they analyzed the regions of this jet images, what they call jet images, essentially like particle collision that creates these images. So they figured out which are the regions on these images that produces the most discriminative power. And they realized that CNN learned features beyond those predicted by physical laws. And they found some of the features, for example, those in this face plane on the lower and in the middle and the lower corner. These features were previously unknown to physicists, and they still don't know how to call them. Okay? So those are the examples where scientists have come up with very innovative ways of discovering knowledge from a deep learning neural network. Have the network learn the data, and then we extract data from this network. from these networks. So I think there's an avenue here, but I call on the community to be creative. These methods are ad hoc, as you can see, but we need to be creative. We need to provide to extract, but we need to give it a shot and try more new methods. If we do not try, the chance of doing this is zero for sure. And there are some of the interpretive methods. For example, we can do visualization. This is one of the figures by Geoscientific, where they find one of the networks is essentially detecting where the face is. You can see where the spaces are. And one part of the hidden layer is essentially trying to track where the layer is. And then you have the visualization. I'm sorry about this being covered up, but this is an LSTM visualization where you can actually estimate, you can actually see which hidden layer responds to a certain neuron, or such response. And you can look at what input caused that response in that middle layer. Oh, that completely messed it up. I'm gonna, sorry. Oh, maybe I shouldn't have done that. All right, maybe I come back. Sorry, this was misaligned. We can do another method is through relevance backpropagation. If you have a decision that's made by a CNN, you can trace it back along the chain of the networks and put it on and project it back to the input space. You can figure out which of the pixels on the input image that led to this decision. This allows us to identify the most sensitive and most mission-critical inputs.
Hey, Chaopeng, sorry to disturb you, but we are seeing
what?
Switching your screen.
Okay, sorry.
Yeah, sorry about that.
All right. I was trying to fix that, but
there we go.
All right. Okay. There we go. And sort of more advanced work is we can train this explanation networks. This is done by computer science folks. I think it's going to be hard for us to do, but what they do is this network can explain this is a white polygon. Not only this is a white polygon, but also why it is a white polygon. Because it is a large white bird with a long neck and a long orange beak. And it can tell you why it thinks that certain objects are what it thinks it is. So these are it's probably hard to do, but we should look into these interpretive methods. And I call on the community to do that. This is the last missing piece. Okay? And how do we incubate such progress as a community? The biggest thing that I think we can get together and do is to do these is to follow the path of computer science and do these open competitions. These competitions are awesome as organizing events of the community. We can greatly leverage the data compilation effort. We can guide separate structural development. We can enhance the culture of reproducibility and comparability. We can evaluate the new models very quickly. We can inherit assets from these competitions, and it grabs a lot of attention. And then we can share resources and models, infrastructures, and very importantly, we need to change our educational curriculum, because none of the curriculum in a PhD study actually prepare our hydrologic students for machine learning. So that needs to be changed to some extent. Okay, so that is my talk today, and on this page I leave some information for you, some emails for Dr. Fan, our GitHub here, my Twitter, and some of the papers. So that's the end of the talk. Thank you very much.
All right, thank you, Chaopeng. I don't see any questions right now, but that was a great talk. Are there any questions from the audience? You can type them in and we'll have Chaopeng respond.
Yeah, we can probably wait a little.
Sure.
Thinking.
So one thing I liked about your presentation about the SMAP information was that your deep learning algorithm was getting the same errors as SMAP does in the highly forested areas. Is there any chance of combining a deep learning algorithm with the SMAP to fill in those gaps?
Let's go back.
Sure.
Oops, sorry, too far. Here.
Yeah.
So you were talking about the gaps between. There are some gaps where they're not applicable. This data, there's no supervising data there. Are you talking about those white gaps in there?
Yes. Yeah, that's right.
Right. I believe like SMAP data is invalid there, and that's why we carved it out. But the thing is, I think the network will produce an output. We can look at that, right? The network will nonetheless provide an output, which isn't isn't shown here because we carved it out to be comparable. But you're right.
Right.
Well, I'm not seeing more questions. Do you mind if I still presenter mode from you to show my slide, Chaopeng, or do you have something else to show?
I guess you can show. Yeah, you can show that slide. But...
All right. Let me take that control away from you.
Yeah, I guess we can give the audience a bit more time.
Yeah. While you're thinking of questions, I just wanted to bring attention to everyone. The last 3 presentations of the Cyber Seminar Series. So next week, I'm going to be butchering his name. Guao Cheng from China, he'll be doing exploring deep neural networks to retrieve rain and snow in high latitudes using multi-sensor and reanalysis data. It'll be at the same time next week, 1 p.m. Eastern. I also want to bring everyone's attention for CUAHSI's 2019 Conference on Hydroinformatics. That will be taking place at the end of July in Provo, Utah, and Chaopeng is one of our keynote speakers at that conference. One of the deadlines we're pushing out is submitting an abstract for an oral or poster presentation by today. You have until midnight to submit your abstracts, and we do offer a limited number of $750 travel grants on a first-come, first-served basis to attend this conference if you're accepted and are presenting an oral or poster presentation. So definitely take advantage of it. Utah Brigham Young University is a very good location. I think this is a very good conference that we have and really good speakers that we have lined up as well. So.
Thank you.
And then if you're not submitting a presentation, I would also definitely recommend just going and attending. Our registration deadlines are June 15th for early bird, and then July 15th just regular registration rates. So I think it looks like we have questions. So I'm going to give you back presenter mode, Chaopeng, just in case you need to show your slides.
Yeah.
All right, this question is from Xiao, a postdoc from Boise State University. He's really interested in the downscaling machine learning techniques. When is the paper coming out, he asks.
Oh, I think that's probably at least three months ago, because we're still training more learning examples. We have a bunch, but we're gonna work on some other watersheds and make sure this actually transfers across watersheds. So probably 3 months, and yeah, I guess you'll hear from us. Actually, if you're asking that question, follow my Twitter, and I definitely make notifications of that.
Okay.
Thanks for the interest. That one, yeah, I believe we're talking about. Oh, so it's way in the back. This one. Yeah, I think this looks promising. Some of the results we're seeing indicates that we do not have to memorize that much, because previously the POD-MM was essentially memorizing, and they really tried to get out of that barrier and try to calculate this reduced order model based on elementary input. So that would be the major advance of this work.
Is there any more specific questions from you, Xiao, on that topic?
All right.
All right. I don't. Should we give one last chance for questions here before we wrap it up?
Yeah, I'll give another minute, see if anyone wants to type in their question.
Okay.
It looks like Chao has one.
Yeah, Chao also wants to know how to consider seasonal variation in that downscaling.
That's a good question. We did not really train separate models for seasonal or different seasons. We trained them all together. We lumped all the data together to train one model. And actually, this is a very valid question. For that, when we did the POD-MM in 2016, we realized that we can train different models in different seasons that work somewhat a little bit better, not too much, a little bit better. However, for deep learning, with our soil moisture task, we try to train this. We try to do experiments where we trained models in one part of the domain, and we train the same model using data from that domain plus data from elsewhere. And this is some work done by Dr. Fang, but we haven't had the chance to send it out yet. We realized that when you have data from somewhere else, it really helps with the training. We call this data synergy effect. It's like when you're training for California, and if you take data from Oklahoma, that data would still help your training in California, even though you have very different environmental settings and soil parameters and all these different settings. Because these networks, because of its depth, it's able to extract the commonalities. My theory is that it's able to extract commonality and identify the differences, and can somehow learn from that commonality. So this suggests that for deep learning models, when you have big data, the best approach is probably just lump all the models, lump all the data, and train them all together to get the best results. So this is a good point. I think that your question regarding the seasonal mode, I have not looked at this, but I suspect probably if we don't do the distinguishing, the difference between different seasons, it would probably even be better. That would be my suspicion, even if we haven't tried it. I'm not sure if that makes sense.
Yeah, that sounds reasonable to me, and Xiao says thank you.
All right, looks like we don't have any more questions, so I think we can wrap it up. Thank you everyone for attending. Thank you, Chaopeng, and hopefully you can attend next week's webinar presentation, same time. So see you next week, everyone, and have a great weekend.
Thank you.